Generative Recursive Reasoning Models, or GRAM, authored by researchers from CAST, Mila, NYU, and Université de Montréal.
Yeah, that's a seriously stacked lineup of institutions.
It really is. And if you're building, training, or deploying ML models, here's the core insight you need straight away. Right now, large language models scale their reasoning by generating incredibly long, token-heavy chains of thought.
Right, which takes up a ton of context space.
Exactly. So recursive reasoning models, or RRMs, they try to fix this bloat by iteratively updating a hidden internal state instead. But existing RRMs hit a massive brick wall.
Because they are purely deterministic.
Yes, they follow one rigid path to a single answer. But GRAM fixes this. It injects probabilistic stochasticity into the latent reasoning process.
Which is such a clever workaround.
I mean, it really allows a remarkably small model to explore a branching tree of multiple hypotheses, right? It naturally scales its intelligence by running parallel trajectories during inference.
And it successfully finds diverse solutions to complex constraint problems, like N-queens and ARC-AGI.
Yeah, it completely changes the game. So welcome to AI Paper Slop. Today, our entire focus is on decoupling reasoning depth from parameter scale.
It's all about making models think deeper, without just making them massive.
Precisely. So to understand why GRAM is such a necessary leap forward, we really need to establish the baseline first.
Yeah, let's look at the continuous reasoning systems we already have.
Right, and figure out why they are, frankly, hitting a wall.
Well, we should start with recent recursive reasoning models, architectures like looped transformers or the hierarchical reasoning model, HRM and TRM.
Right.
The appeal of these systems to an ML engineer is pretty obvious. Normally, to get an AI to execute complex reasoning, you either need a massive parameter count or you force the model to output a massive string of intermediate chain of thought tokens.
Yeah, just spitting out tokens over and over.
Exactly. RRMs decouple reasoning depth from parameter count by using shared transition functions repeatedly over time. They create deep computation without outputting intermediate tokens.
Okay, so let me make sure I'm visualizing that correctly. Instead of passing data through, say, 100 unique transformer layers, you have one transformer layer or like a small block of layers, and you just pass the data back through that exact same block 100 times.
That is the core mechanism, yeah. By applying those shared blocks repeatedly in a loop, you build computational depth natively within the latent space.
Interesting.
So you get reasoning capability emerging from the organization and repetition of the computation, rather than just relying on a giant model or spitting out intermediate tokens to a scratch pad.
Okay, so to use an analogy, standard chain of thought is like solving a math problem by writing every single tiny step on a massive whiteboard.
Right, you can see the work, but it takes up a ton of physical space.
Yeah, or in our case, context window and autoregressive generation time. But RRMs, on the other hand, are like a chess master, silently running through dozens of board states entirely in their head.
Oh, that's a great comparison.
The depth of thought increases, but the brain size stays the exact same.
The visual of the chess master calculating silently works really well here. The model just computes internally, updates its hidden state, and then finally generates the answer.
Okay, let's unpack this, though, because if running these latent loops is so incredibly efficient at saving token overhead and parameter bloat,
right,
why aren't loop transformers dominating every leaderboard right now? If I look at the state of the art, everyone is still using massive autoregressive models. There has to be a catch to the RRM approach.
What's fascinating here is that the catch lies in how they navigate complex problem spaces.
Okay.
Existing RRMs are entirely deterministic. Given a specific input prompt and a specific initialization state, an existing RRM follows one single latent trajectory.
So they just lock onto one path.
Exactly. They collapse all plausible reasoning paths into a single attractor. They just can't maintain uncertainty.
Now, collapsing into a single attractor sounds like physics jargon. What does that actually look like during inference?
Okay, think of the problem space as a vast, uneven landscape of hills and valleys, where the deepest valleys represent the best, most logical solutions.
Okay, I'm with you.
A deterministic model operates like water rolling down a hill. Once it picks a groove, gravity relentlessly pulls it to the bottom of that specific valley.
So it can't back out.
Right, it cannot suddenly decide to flow uphill to see if there's a deeper, better valley just over the next ridge. If the deterministic model takes a slightly wrong conceptual turn early in its latent loop, it gets permanently trapped in a suboptimal trajectory.
Which means it has absolutely no mechanism to explore alternative strategies.
None.
If the problem is ambiguous or, if it's a constraint satisfaction task where multiple valid solutions exist, it's just stuck in whatever valley it rolled into first.
Yeah, that deterministic recursion leaves probabilistic, multi-hypothesis reasoning completely unexplored within the RRM paradigm. And this is the exact bottleneck the researchers set out to solve.
Because a capable reasoning system needs to maintain uncertainty,
Right.
And it needs to consider alternative hypotheses, not just blindly rush down the first hill it sees.
Exactly. Which brings us to what the researchers actually built.
Right. So knowing that deterministic loops fail because they get stuck in one valley, how do you actually turn a single, rigid, latent track into a probabilistic, multi-trajectory computation?
They approached this by giving Graham a hierarchical multi-scale structure. They divide the latent state into two distinct components.
Okay, what are they?
You have a low-level state, denoted as LT, and a high-level state, denoted as HT.
Wait, why complicate it with a split? If the goal is just to create diverse reasoning paths, couldn't you just add noise to the entire latent state at every step? Like just inject randomness everywhere to force the model to think differently?
Well, if you inject unstructured noise across the board, you destroy the model's logic. You don't get diverse reasoning. You just scramble the math and get gibberish.
Oh, I see. Because it forgets what it was doing.
Exactly. A reasoning system has to track strict, granular constraints. If you scramble the entire state, the model forgets the rules of the puzzle it is trying to solve. So Graham handles the two components differently.
How so?
The low-level component, LOT, runs purely deterministically for a set number of updates, what the paper calls K-updates.
Oh, so it acts as the mechanical memory. It keeps track of the absolute facts, like an accountant rigidly ensuring the math actually adds up step by step.
The accountant metaphor is perfect here. The low-level state is rigidly following the rules. But then we have the high-level component, H-T. This is where the stochastic guidance signal is injected.
Okay, the randomness.
Right. This signal, denoted as epsilon, is modeled as reparameterized Gaussian noise.
Let's pause on reparameterized Gaussian noise for a second. For a listener who hasn't stared at a statistics or deep learning textbook recently, how does random noise magically turn into a strategic driver? Random noise is just static, isn't it?
It starts as static, yes. But the reparameterized part is the key mathematical trick. In machine learning, if you just use pure random noise inside a network, you can't calculate gradients through it.
Oh, because the backpropagation algorithm breaks down.
Exactly, which means you can't train the model. Reparameterization separates the randomness from the learned parameters. It allows the neural network to learn how to shape and interpret that noise.
That's super clever.
Yeah, during training, using a technique called amortized variational inference, the model learns to map that raw noise into meaningful, diverse strategic directions.
So amortized variational inference is basically teaching the model how to guess the most promising reasoning paths, rather than just calculating every single possibility from scratch or flailing wildly.
Exactly. It learns a distribution of good strategies.
It learns to intuitively leap to promising areas of the problem space.
So the high-level state becomes the manager. It takes that shaped noise and says, what if we try this completely different approach? It provides creative, strategic nudges.
And then the low-level state, the accountant, takes that nudge and rigorously applies the constraints of the problem over the next case steps.
Yes, to see if the manager's idea actually holds up to logical scrutiny.
That is a brilliant division of labor. And if I'm reading the architecture correctly, the decoder, the part of the model that actually generates the final output for the user, is designed to only read the high-level component.
Yeah, the low-level state does all the heavy lifting of constraint propagation internally, hidden away. The final decision is drawn entirely from the strategic high-level trajectory.
Because the low-level state handled the messy math, the high-level state can just focus on the ultimate conclusion.
Right.
This fundamentally changes how we deploy compute, doesn't it? We are shifting the heavy lifting from training time scaling to inference time scaling.
It's a huge paradigm shift.
And here is where it gets really interesting for anyone deploying these models. You can now scale the intelligence of your reasoning system simply by sampling more trajectories in parallel.
Yeah, if you have the compute budget, you don't need a bigger model. You just run dozens of alternative hypotheses simultaneously.
Unlocking parallel trajectory sampling is massive. But wait, it introduces a serious resource problem.
Yeah.
If you spin up 50 parallel thoughts, you need a way to manage them efficiently, right?
You definitely do. You can't just have them all running infinitely, eating up your GPU budget.
Yeah, your AWS bill would be insane.
Exactly. This is where Graham uses two vital mechanisms, the latent process reward model, or LPRM, and adaptive computation time, or ACT.
Okay, walk me through how those two mechanisms actually function together. Because if I ask the model what 2 plus 2 is, I don't want 50 parallel processes digging into deep search trees and wasting electricity.
Right. So the researchers use a value head, denoted as VPI of ZST, to predict the expected accuracy of the final output based solely on the current latent state.
So this value head is the LPRM.
Yes. It evaluates a specific reasoning path and scores how promising it looks at that exact moment. But the clever part is the halting probability, Q-halt.
What does that do?
Using a Q-learning formulation adopted from earlier reinforcement learning models, each parallel trajectory evaluates its own state and can choose to terminate independently.
Let me challenge that for a second. If a trajectory can just decide to stop when it thinks it has the answer, doesn't that risk it halting prematurely on a good enough but ultimately flawed answer?
That's a valid concern.
Like, how does it know it is actually done and not just stuck in a shallow valley like we discussed earlier?
Well, the Q-learning formulation prevents that. Q-learning calculates the value of taking a certain action. In this case, the action is either continue thinking or halt.
Okay.
During training, the model is penalized for halting on wrong answers, penalized for taking too many steps, and rewarded for halting on correct ones efficiently.
So it learns the balance.
Exactly. So the halting probability isn't just a blind guess. It crosses a threshold specifically when the sigmoid of Q-halt is greater than 0.5, only when the latent state strongly correlates with the high probability of correctness according to the LPRM.
Okay, so because these trajectories are running in parallel, one path might hit that 0.5 threshold and find a solution at depth 3. Meanwhile, another path, tackling a more complex facet of the problem, might need to dig down to depth 15 before it is confident enough to halt.
Yes, it dynamically allocates compute based on the difficulty of that specific reasoning trajectory.
This is huge for resource management. Let's connect this directly to your day-to-day as an AI researcher or ML engineer listening to this. You can dynamically allocate your inference budget per problem complexity.
You don't have to burn massive compute on easy queries just because your model has a fixed massive size.
Right. You spin up more parallel samples for hard queries and let the easy ones halt early. It mirrors human deliberation. You think longer and consider more options when the stakes or ambiguity are higher.
It is an incredibly elegant way to optimize inference costs while maximizing reasoning performance.
The theory sounds incredibly elegant, I'll give you that. A strategic manager and a mechanical accountant working together, dynamically halting when they solve the problem. But the ML graveyard is absolutely full of elegant theories that completely break during inference. Did they put this up against an unforgiving benchmark?
Oh, they definitely did. The benchmark results are striking, particularly when looking at constraint satisfaction tasks. They tested this on n-queens and graph coloring.
Oh, nice. For anyone who hasn't touched n-queens since like an undergrad algorithms class, it is the classic puzzle where you have to place n chess queens on an n by n board so that no two queens threaten each other.
Right. And the key thing there is that there isn't just one right answer. There are multiple valid configurations.
Right.
For deterministic models like loop transformers, HRM, and TRM, this is a nightmare scenario. Because they are deterministic, they try to find a single path that represents the average of all the valid configurations.
Which is impossible.
Yeah.
It is like trying to average a left turn and a right turn by driving straight into a tree.
Exactly. They converge to a single broken prediction or crash entirely, leaving multiple valid solutions completely unexplored.
Ouch.
Graham, however, discovers multiple unique valid solutions. On the n-queens and graph coloring benchmarks, Graham achieves 99.0% validity.
99% validity is wild. But how does that compare to architectures specifically built for probabilistic generation? I'm thinking of diffusion models, which are literally designed to generate diverse outputs.
They actually compared Graham against a heavy diffusion baseline called D3PM, which is a discrete denoising diffusion probabilistic model.
And how did it do?
A 55.1 million parameter D3PM only achieves 79.2% validity.
Wow.
Graham hit 99.0% validity with only 10.9 million parameters.
So a model 1/5 the size is absolutely crushing the diffusion approach. Why is that? Is it because diffusion operates in token space, which is just clumsy for hard mathematical logic, whereas Graham's latent space is purpose-built to track constraints?
That's exactly it. Diffusion models, which add and remove noise from discrete tokens, struggle immensely to maintain the strict global rules required for constraint satisfaction.
Makes sense.
Graham separates the strict rules from the creative noise using the low-level and high-level split we discussed earlier. But honestly, the real stress test in the paper is the ARC-AGI challenge.
The abstraction and reasoning corpus. This is Francois Chalet's benchmark designed to test true abstract reasoning and generalization, not just rote pattern matching.
It's notoriously difficult.
Yeah, you're given a few visual grids demonstrating a transformation rule, and you have to apply that unseen rule to a new grid. Usually you need massive external data augmentation to even get a foothold on ARC.
Right. Models usually rely on generating thousands of augmentations for a single problem and doing majority voting. The researchers wanted to isolate the specific effect of Graham's internal generative sampling, so they tested it on ARC with 0 external data augmentation.
0. That's brave.
And the results showed that even with 0 augmentation, accuracy consistently climbs simply by generating more parallel samples internally.
Let me make sure I'm getting this. Are you saying the model is generating its own internal diversity? It isn't just reacting to diverse inputs provided by an external Python script. It is genuinely exploring the hypothesis space from within.
Yes. It proves the core hypothesis of the paper. Parallel sampling allows the model to recover from initial errors.
How so?
If you have 50 parallel stochastic trajectories and one path hits a conceptual dead end in the ARC-AGI problem space, another path might have taken a slightly different strategic nudge from the high-level manager state that easily bypasses that trap.
It is survival of the fittest, but for latent thoughts. And the LPRM value head helps bubble the most promising of those surviving thoughts up to the surface so the decoder can actually print the winning answer.
The LPRM acts as the evolutionary filter, yes. It confirms that probabilistic multi-trajectory recursion is a highly efficient, necessary design principle for the next generation of reasoning architectures.
What the researchers behind Graham have shown is that by decoupling the strict deterministic constraint tracking from the stochastic creative problem solving at the hidden latent level, you can build incredibly compact models.
Models that punch way above their weight class.
Right. Models that scale their intelligence entirely at inference time. You don't need 100 billion parameters if your 10 million parameter model can effectively think in 50 different directions at once, track the math perfectly in the background, and recognize the right answer when it sees it.
It suggests the broader field might be neglecting a much more efficient dimension of scaling.
Absolutely.
We have been so focused on scaling up model parameters and sequence lengths, but the width and diversity of internal latent computation might be the key to unlocking actual reasoning.
Which leaves us with a final, somewhat provocative thought to ponder as you go back to your own code bases.
Lay it on us.
We have spent the last few years totally obsessed with getting models to show their work by printing out massive autoregressive chains of thought in English text. But if advanced reasoning can be completely decoupled from token generation, if it can be scaled probabilistically within a compact, silent, latent space, are we currently wasting billions of parameters and massive amounts of GPU compute in autoregressive LLMs just to print out intermediate text?
That is a fascinating question.
Could the future of frontier AI be surprisingly small models that just think longer, deeper, and more randomly in a silent, latent space before ever speaking a single word?
It is a really compelling vision for the future of inference.
It really is. Thank you for tuning into AI Paper Slop. We highly encourage you to check out the full paper, Generative Recursive Reasoning Models for the exact loss formulations, the amortized variational inference math, and to dig into their code base. We'll catch you next time.